Another famous space-filling curve is Hilbert curve. Hilbert curve is constructed by successive iterations of subdividing subscales into 4 smaller subscales. The smaller subscales are connected by rotation and reflection of the fundamental image given in the first square. The basic idea of the proof that HEC is space-filling is that even the maximal distance between a point in the subscale and HEC in the subscale is 0. Thus, the distance between any point in the subscale and HEC in the subscale is 0. Thus, the square and HEC are equal. Upper middle panel in the figure shows the most distant points in the subscale from HEC are the corners marked as a black dot. After nth iteration, the distance between the black dots and nearest point in HEC is square root 2 multiplied by 1 over 2 powered by n plus 2. As n becomes large, the distance becomes smaller, and it can be smaller than epsilon for any arbitrarily small epsilon larger than 0. Thus, because epsilon is arbitrarily small, the limit is 0. Therefore, the distance between any point in the subscale and HEC in the subscale is 0 as n becomes infinite. Therefore, HEC is space-filling, supporting Cantor's earlier argument that a line has the same dimension as a plane. The key in the proof is that limit 1 over 2 powered by n is 0. However, in video 2, it was shown that limit 1 over 3 powered by n is larger than 0. Thus, limit 1 over 2 powered by n is larger than 0. Therefore, HEC is not space-filling. Even the shortest distance between the border of the subscale and HEC in red arrow in the figure is not 0. And we have another proof. The points of HEC on the grid in green are a proper subset of the set T, which is an element in unit interval where x multiplied by 2 powered by I is a natural number. As in video 10b, irrational numbers cannot be in T, as you see here. Therefore, the number of points in the grid is larger than the number of points of HEC on the grid. Thus, HEC is not space-filling. The cardinality of a plane is larger than that of a line, such that C squared is larger than C. Cantor assumed that any real numbers can be expressed in binary digits by the concept of Cauchy sequence and Cauchy completeness. That C equals 2 to the power of RF0 is a corollary of his assumption that any real numbers, including irrational numbers, can be expressed as RF0 sequences of binary digits. If C equals 2 powered by RF0, then C multiplied by C equals C. Thus, this cardinal arithmetic appears to corroborate the above Cantor's counterintuitive conclusion that the number of points in a real number line is equal to the number of points in a plane. However, C squared is larger than C, which contradicts the assumption that c equals 2 to the power of -no, and that any real numbers can be expressed in binary digits by the concept of Cauchy completeness. Please send critical comments to this address. Thank you very much.